In this video, I'm going to go over how to do the homemade battery lab. So the battery is basically going to be made from a couple different materials, and I'm going to put them all into a Ziploc bag and give them to you, and it's going to be your job to figure out how to build the battery using materials that you may not normally think of as a battery. So this picture here is actually the battery that you're going to build, but the pieces of material aren't always going to look like what they look like here. Like these big containers, which you're used to using, we're going to use Petri dishes, and for copper, we're going to use a penny, and for zinc, we're going to use a bar of zinc metal, so that will actually look like what it's supposed to. The voltmeter doesn't actually look like this, and so you're going to be building the exact battery that's here and explaining to me how it works, but you're going to be using real-world materials, so it's going to look a little different from what you're used to. So the salts that we're using are going to be copper 2 sulfate and zinc nitrate. And so the copper sulfate is here in half cell 1, and the zinc nitrate is here in half cell 2. And so that's what you're going to do. Now, when you get the battery and you actually put it together, you're going to draw it out. But before we do that, what I want you to do here is actually complete the battery, meaning what does copper sulfate break up into? Show me which one is the anode, which one's the cathode, which one's going to get fat, which one's going to get skinny, what's the purpose of the salt bridge, which way do the electrons flow. I want you to draw everything in this just like it was a practice problem for batteries. Then when you get to, then after you do that, that will actually make it easier for you to build the battery, because once you know how it works, it should be easier to assemble. Now when we get to the second page, here's where you're going to draw out the diagram and label everything. In other words, it's one thing to have it labeled on here, but now I want you to transfer all that labeling onto your actual diagram where the things are maybe a little bit different. So here you're going to draw out the diagram. Now, if you're virtual, it's going to be, I'm giving you a picture of the built battery. Unfortunately, you don't get to build it. If you're in class, you're going to build it using the equipment, and then you're going to label everything that's here, okay? If you actually are building the battery, you're going to have to clean and dry and put away the equipment. And if not, you just obviously move on to the next part. So you're going to draw it as you see it here, meaning I don't want to see another diagram that looks like this. I want to see, well, okay, what does the voltmeter actually look like? And since we're using a penny for the copper electrode, well, we're going to actually draw the penny and the wire connecting it. I want you to draw it as is. It doesn't have to be art, but it does have to be at least somewhat recognizable. Then there are a couple questions, and these questions, if you know how to do the battery problem on the first page, should be easy. Which metal was losing electrons? What's that process called? Write the two half reactions. You can put them here and here. So put one over here, one over here. This isn't a half cell or a big mono cell. This is just a space to draw the battery. So you can draw your half reactions here. And then let's go to the last bit of questions, and that's pretty much the whole lab. So how did you know which metal was gaining electrons? What's that process called? Obviously, we should know Leo and Gur at this point. Write the half reaction for the metal that was reduced. Which electrode gains mass? Which one loses mass? We know the red cat gets fat. The anox loses weight. And then what type of energies do batteries convert? It's either chemical to electrical or electrical to chemical. State your evidence that confirms your answer. That should be pretty simple. And then the practice problems are from this point on. So what you're going to do is you're going to take this reaction, and you're going to you're going to assign your oxidation numbers, which you should know how to do already. Once we know our numbers, you're going to look for the two that change. In this case, chlorine changes. And oxygen changes. Oxygen lost, I guess I'll put it over here, lost 2 electrons, which is Leo, lose electrons oxidation, and chlorine gained 6 electrons. Now this one throws people off because you got to remember it went from +5 to 4 to 3 to 2 to 1 to 0 and then to -1. So it actually gained 6 electrons, so be aware of that. And then when you do your two half reactions, they shouldn't be too bad. The reduction half reaction was chlorine, so remember, we only draw it for a single atom. I don't care that there is only one chlorine on each side, but it will matter more for oxygen. And then for oxidation, So I only drew it for a single oxygen atom. That makes our math much easier. And then we have to figure out our multipliers to balance it. So the first common factor between 2 and 6 is actually 6. So if I multiply this one by 3 and then just that one by 1, I'll bring them both up to gain and lose 6. And so we're done with the multipliers. And then type of reaction. Well, this type of reaction, in addition to being a redox reaction, is also, we can call that decomposition because we are starting to break down the KClO3. It's not true decomposition because we didn't break it down into individual K, Cl, and O, but it is close enough. So I would accept redox, obviously, because this is definitely a redox, and I would also accept decomposition. So now for the rest of them, you're just going to keep going. So there's a bunch of reactions. You're going to tell me the reaction type. If you notice on this one, at the very top, I didn't tell you the reaction type, or I didn't ask for the reaction type, and the reason is simple. Since I'm not showing you the entire compound, I'm only showing you the elements that do changes, right? And technically, I guess it's called a net reduction oxidation equation, but whatever. So since I'm hiding everything else from you, you couldn't possibly identify the reaction type, so I didn't bother to include it here. But then I picked it back up here, here, and here. And yes, there's a lot of these. 3 more on this page. And then some extra problems. I don't actually think I have this on the back of your lab, though. I will say, let's see. 1, 2, 3, 4, 5. Oh, I do have this included. So then for this page, you're going to do the single replacement reactions for the following. This should be pretty easy. The only extra step involved is you're going to have to figure out if the elements swap trade places or not. And to do that, you are going to need table J. So you go to table J. If BA is higher than NA, then they trade. If they are not, then if BA is lower than NA, then you write no reaction and you don't have to do anything. If you don't know how to do these, you're going to have to go back to your video, but I'll do one with you. So if we take a look at table J, just to be sure, because I don't have table J memorized, because I can always look it up. Let's do the second one down. Mg is above H on table J. Now granted, on table J it's H2, but any H will do, so H3 works as well. So in this case, Mg, since it's more unstable, is going to trade places with H. So that means H is going to come out, but when it comes out as H2 because it's a diatomic. And then Mg goes in, and PO4, it's going to have to be crisscrossed. So PO4 as a polyatomic is -3. Mg is +2. So when they get crisscrossed, they get the formula Mg3, PO4 twice. So there's my formula. Now, in order for the rest, I have to assign oxidation states. 0. Now I'm going to save time. I'm just going to put PO4 as -3, +1, and 0. The reason I did that, I could find the individual O and the individual P. The O we have a rule, the P we can solve. That's not impossible. But since PO4 didn't break up and it didn't do anything, I know it's not the answer, meaning it's not going to be doing redox because it stayed PO4 on each side, so it doesn't actually change. So that's why I can kind of go a little bit faster and just say, okay, PO4 as a group's -3, because I'm really concerned about what's bonding to PO4. That's the real issue. So now I found my 2. H went from +1 to 0, so that means it gained 1 electron, and Mg went from 0 to +2, so it lost 2 electrons, which is LEO, lose electrons oxidation. So now let's do our 2 half reactions. So Mg0 turned into Mg +2 by losing 2 electrons, losing them because they're on the right. And then H, a single H +1, gained a single electron and turned into H0. Now again, notice I don't care that there's 3 of them here and that there's 2 and 3 here. When we do half reactions, we only do them for a single atom. It's much less complicated. And then to make these equal, I just multiply this by 2 and that by 1. And then for balancing purposes, now that's a little bit harder. To balance this guy, I'm going to have to what am I going to have to do? I'm going to have to put a 2 here because the PO4s are 2. That's going to give me 6 H's, so I'm going to put a 3 here. That gives me 6 H's, and then I need 3 mGs, so I put a 3 there. Once I do that, this becomes a 1. My balancing is done, and then spontaneous or non-spontaneous. Well, here's a hint. If it's spontaneous, or if the reaction happens, then we call it spontaneous. If the reaction does not happen, if there were no reaction present, then it would be non-spontaneous. And what that means is you can make the reaction happen by adding electricity and actually forcing the reaction to go reverse, the reverse way that it would naturally want to, but it's not a spontaneous event. It won't happen on contact. You're going to have to hook it up to a power supply and turn it on in order to make it go backwards. And that's everything you need for this lab.